July meetup. Today's meetup is a second workshop on A/B testing led by Professor Feit and Ron Berman. Please feel free to live tweet this event with @RLadiesPhilly or #RLadies. As usual, we want to thank RLadies Global to support this friendly community. Could you hear me?
Mm-hmm.
Have I started earlier that you heard me?
Yeah, we heard everything.
You for a second.
All right. So because I just self-mute myself. So the RLadies is a worldwide organization to promote the gender diversity in our community. Everyone is welcome to attend our meetups and mentorship programs as far as she or he supports our code of conduct. Please refer to the link below for more details. So as a before the meetups, we have a few announcements we want to make. First is about the Maya community. This is a community that we recently recognized that trying to provide a community for the underrepresented minority users of R. It provides the support for the people who identify themselves as the underrepresented minority R users. So you can follow them through the Twitter handle here. If you are interested in joining, you can also complete the community registration form through the link show up on the slides. I think our co-organizer can send a link on the chat for them to click. So the second announcement we want to mention is that our member, Jake Riley, has recently had 2 packages now on the CRAN. One is the simple color, which gives you the access to the constant set of colors. Is really similar to the palette tool that you might have been used with the Microsoft Word. You can see colors in the same way that you use the names use the name to color the text or the chart elements. The second object is a shining objects. So the shiny object allows you to debug the shiny and the reactive R markdown. So Jake will take talking more about this, about the shiny objects in the full meetup. So we're very looking forward to that meetup. Besides that, we also have a mentor speaker directory. I think that we mentioned the last time, but we just want to re-emphasize this again. So if you are interested to give a talk in our meetup or would like to join our meetup program as a mentor, please sign up through the link. Also, if you want to just pair up with mentors or to learn R or pursue the career advice, you can also go to this link to find the mentors' contact information. And our ladies can help you to pair up with your mentors. And if you have any questions, just shoot us an email. All the information is on this directory as well. And also, we are really excited to announce that we have our own YouTube channel now. Since the pandemic, we have started record our online meetup events and post them on the YouTube. This channel includes the first workshop on the A/B test. So if you missed the first one, go to our YouTube channel. We're also recording this event as well, and we'll finally put on the YouTube channel. You can find all this information on the RLadies blog. Also, we want to mention we have 2 future events planned out already. One is August about the machine learning workshop, and September about the decision tree and the random forest. Remember the date and go to our meetup page and sign up. Now let's start our workshop by introducing our two speakers today, Dr. Elea Feit and Dr. Ron Berman. Elea is an associate professor and Drexel, and if you attend our first A/B testing workshop, and you probably know her, she's a really passionate teacher. Ron is assistant professor in the Wharton School from Penn, he and Elea both working on a project, not project, actually is a method called the test and roll that we will cover today is an alternative way to do the A/B testing. So they published a paper in the Marketing Science 2019, and I put the link here. If you're interested, you can go to the link and read the full paper. Today's workshop, all the materials that you can find through the link, and we will put this link on the chat so you can have it like easy click. One thing I want to mention is that we using a Q&A Google Doc. So we highly suggest to put your questions on this Google Doc so we can monitor the questions much better. And at the end of the workshop, we will write a recap and share this Google Doc through our blog. So you basically use this as a note taken by the group. And now I'm passing the screen to Elea. And thank you for joining our ladies and present the workshop.
Great. Thank you very much, Tun. Ron, you should probably say hello since you're here.
Hello, everyone.
I'll be doing most of the presenting, but since this is a project that Ron and I have both put thousands of hours into, probably between the two of us, he's here to answer questions. So he'll be in the Q&A doc answering your questions. I might ask him a few questions as we go. We'll see how it goes. So before I jump in, I should give a little thanks to Drexel and Wharton. So, and I wanted to make you aware of a couple things that are going on at Drexel and at Wharton. So at Drexel, I teach in two master's programs, one in business analytics and one in marketing. And I actually teach an elective in A/B testing for both of those programs. And you can apply to be in those programs starting 9/15, and maybe you'll actually get to come to campus at some point during your 18-month program. We also have a business analytics meetup that a lot of folks here might be interested in. That's open to everyone. It's kind of a fun chance to get to meet our students. So we bring in speakers that would be of interest to our students in the program, but we also make that open to anyone in Philadelphia who wants to attend those events. And last on the Drexel side is if you're interested in partnering on research with Drexel, we have this program called the Drexel Solutions Institute that is kind of develops partnerships with companies, everything from exec ed, recruiting undergrads, recruiting grad students, all the way to sponsored research. So you can follow that link. Do you want to talk about the ones on the Wharton side, Ron?
Sure. So very briefly, we have two programs running in executive education, both online currently. One of them actually you can come to class when it's running in class. The first one is in digital marketing. It covers digital marketing more broadly, and A/B testing is one part of it, but it's kind of how to use data and combine it with marketing. And the other one is more broad about customer analytics, what is prescriptive analytics, descriptive, predictive, and how to use data to inform decisions. The last link, which I think is interesting, is analytics at Wharton. This is more of a kind of a school-wide initiative that started a few years ago that kind of is an umbrella organization for all of the analytics organizations at Wharton. We have a new one focusing on AI. We've had worked in customer analytics for quite a long time, etc. So if you're interested in analytics generally and combining data with decisions, my focus, of course, is on marketing, but it actually looks into also people analytics and other types of analytics. I highly suggest you take a look.
Great. So sorry about that little advertisement, but fortunately or unfortunately, Drexel and Wharton pay our salaries, so we wanted to give a little thank you to them. So I'll just jump into the workshop material right now. So we're going to talk today about A/B testing, and I want to make sure we're all level set on what A/B testing is. So the idea behind A/B testing is that you have a bunch of customers or users or sort of people that you're interacting with. They might be getting an email or visiting a website. They're somehow interacting with you as a company. And so what you want to do is take all those potential people, in this case, the example on the slide are visitors to your website. And as they arrive at your website, you toss a coin or a virtual coin really, and half of those people see one version of your website, the green version, and half those people see the blue version. And the reason you do that coin toss is that makes the groups on average equal. So if you do that randomization across a large number of visitors, the percentage of people who are women and the percentage of people who are, have a high school degree and all of those other kinds of demographics that you might look at are going to be on average the same between the two groups, which makes it a fair comparison between the red group and the green group. And then what you do is you measure some kind of response. It's actually kind of a tricky thing that we won't talk about tonight of deciding what it is you want to measure. In this case, we're measuring conversion, which is just digital marketing speak for something good happened. Could be a sale, it could be that they clicked on a link that you wanted them to click on, something good happened. And you can see the green group had 21% conversion and the blue group had 38%. So we have clear evidence that the blue group is a better option. The other type of experiment that actually Ron and I work with quite a lot is it's sort of a variation on this. So you might have some kind of active treatment, like sending people an email or sending people a catalog. And then you compare that to a randomized control group, or in marketing, we call that the holdout group, and they don't receive the marketing action. So in this case, we have people who received emails and people who received no emails, and we're measuring the revenue per customer for each of those groups. And you can see the people who actively got the email bought $15.38 on average, and the people in the holdout group bought $9.15. So we can actually call the difference between those two the incremental lift of the advertising. So that's another type of A/B test that you might be working with in marketing. So that's just kind of level setting everybody. The goal of the session today is to introduce you to an alternative way of planning and analyzing an A/B test. This is, I think Ron and I were the first people to think about this in terms of A/B testing, but it's based on a long tradition called Bayesian decision theory, which has, been around since the 60s, of how you think about making decisions under uncertainty. So we just took those basic ideas and applied them to A/B testing. I can say that now that the paper is published, right, Ron? We don't have to brag that this was something completely new that we invented. So we actually think this has a lot of advantages over the approach to A/B testing that I talked about in the last workshop, the traditional hypothesis testing. So we actually gave it a name. We call it test and roll. We are marketing professors, so we have to have good branding for things. So we took an old idea, we applied it to a relatively modern problem of A/B testing and gave it a brand name, test and roll. And I want to walk you through how you could run your own test and roll. So my goal is that everyone in the workshop today will walk away with the knowledge of how to set up an A/B test using this framework, because really ultimately Ron and I really want people to run A/B tests following this approach. Sorry, I keep losing the active window. You got the links in the chat for the materials, so you can follow along with the slides. Those are just HTML slides that you can page through as I'm going through, and almost all of the code is on those slides. So if you are unfamiliar with R Markdown, or it's just been a long day, you should just follow the slides. And you can either watch the Zoom screen, or you can, if you like flipping around to see what came before and after, you can follow the link to the slides. If you actually want to run the code, all of the slides were created in R Markdown. So here is the R Markdown file that for the slides that you were just looking at. So I write the slides in R, and then I click knit, and it creates the HTML slides that we were looking at before. And then when you get to these code chunks, you can run them. So you just hit the little green play button in RStudio, and then you'll be actually running the code that I'm talking about. And there are a few instances where I don't show all the code, and so if you wanted to see those details, you would want to get that R Markdown file and be looking at that. And just a few things of what I expect everyone here already knows. You know, you have to start somewhere. And so I'm gonna assume that you know what an A/B test is, because I just told you what an A/B test is. It's really not a complicated idea. But if you have questions, ask questions. I'm also going to assume that you know what a probability distribution is, like the normal distribution, but ask questions if you have questions about that. And I'm going to assume you're comfortable reading R, and I'm going to use R for math calculations, for loops, and for plotting. But, you know, ask questions about that as well. So, and there's lots of people available in the chat. Both our ladies organizers and Ron will all be in the, sorry, I said chat, but I mean the Google Doc. So you can ask a question there, and one of them will answer it. And I do not expect that you know anything about how to use a hypothesis test. In some sense, it's better if you don't know how to use a hypothesis test. Because if you, I've taught Bayesian methods a lot of times before, and if people try to think of them by analogy to frequentist methods, they tend to get very mixed up very quickly. The problem is that Bayesian methods are very similar to frequentist methods on the surface, but at a very deep level, they're different. And so it's hard, you think some knowledge is going to transfer from one to the other that doesn't. And so anyway, I'm not gonna talk too much about it until the very end. I'll give some comparisons of the two approaches. And if you wanna learn more about hypothesis testing, just watch that video on the YouTube channel. All right, so now, are there any questions about logistics that have come up?
No questions about logistics, but there is a question about A/B testing.
What is it?
How often is it being used? Is it very popular or not? And can you even tell if you're being A/B tested or not?
Oh, people want to know if they're being A/B tested as a user. I actually have been teaching this for about 10 years. I would guess that almost all large organizations like a Facebook, Google, Amazon, all the big tech companies are doing a lot of A/B testing. It's kind of built into their platforms, but you're also starting to see it quite frequently among smaller marketers and advertisers. Tools like Constant Contact or MailChimp have A/B testing built into those email tools. There are A/B testing tools for mobile apps. I would guess, like, of large marketers, 100% are doing it. Of mid-sized marketers, probably 80%, and small marketers, maybe a third. What do you think of those guesses, Ron?
Yeah, I would guess they all use it. I think from like a user perspective, you're probably participating in a test multiple times a day, easily.
Oh yeah, and I wanted to tell my little story. So I live out in the country. So I buy fruit trees from time to time from Stark Brothers Nursery. And one day I got an email from them that said, A/B test setup trial. That was the subject line. And so I responded to the email and I said, I see you messed up in planning your A/B test. No harm, no foul. I'm a teacher, I teach this stuff. If you have any questions, feel free to email me. And the poor kid, he's like, that was the first A/B test I ever tried to send and I messed up and I feel really bad. And I said, no, don't worry about it. Like, just keep going, because the idea is that this becomes an engine of innovation for your marketing program. So you have an idea, you know, maybe Ron and I have two different ideas about what the subject line on the email should be. You run it as an A/B test, and then you start to learn what is it that your customers respond to. So I would guess that as a regular web user, you're probably in dozens every day.
There are two more questions, more technical about A/B testing, so I'll just answer them in chat in the Google Docs, and I think we can continue. Okay.
Great, thanks. All right, so we're going to start by talking about how to analyze an A/B test using Bayesian inference. The paper that Ron and I wrote is really about planning the A/B test, but I thought it would be good to give you the background on how to analyze the A/B test so that you had some idea about that as well. So let's start with that. It's usually easier to think about analyzing the A/B test before you think about planning it. So let's imagine we had data from an A/B test. Well, let's not imagine. We have data from an A/B test. So there's two groups, A and B, and we're comparing the time users spent on the website for two different versions of the homepage. So people come to your homepage, they get assigned to A or B. Maybe it's two different pictures or two different taglines or a different placement of a button. But we have these two different versions. They're in the data frame test data. And if we summarize those by group, I can compute the mean and the standard deviation and the number of observations in each group. And we can see that in the A group, we had 500 people and their average time on site was 5.33. And in the B group, we had 500 people and their average time on site was 5.36. So, and this is kind of typical. You'll run an A/B test and you get data back like that. It's not like I'm gonna call the CMO and say, oh, B is the answer, right? Because they're pretty close. So we need to do a little bit of statistical inference to figure out, like, looks like B is better, but how sure are we that B is better? Because we've only seen 500 visitors and they have kind of close averages. So if I'm going to be Bayesian, I'm always going to start with prior beliefs. So my goal is I want to know what the mean time on site is for the A group and the B group. Obviously, each person is going to be different one from the next, but I want to know on average, how long do people stay on the site when they see the A version, and how long do they stay on the site when they see the B version? And before I saw this data, like let's imagine I hadn't even seen the previous slide, I know nothing about how long people might spend on the website. They might stay for 5 seconds, they might stay for 5 hours. And I can actually like take those beliefs and quantify them with a probability distribution. And I'm going to use the probability distribution normal with a standard deviation of 100 and that's in minutes. And I'm kind of thinking like, what's the longest you could ever spend on a website? Maybe 300 minutes, that seems kind of like the longest you would ever spend on a website. I play with normal distributions a lot. Maybe you don't, so it might be easier to see a picture. So this is my prior beliefs about how long people might spend on the site. And you can see it kind of runs from about minus 300 minutes to 300 minutes. This is the point where I should be getting tons of questions, and it already did. Thanks, Bill Deutsch. I don't know you, but now I know you. Yes, my prior is kind of wrong in that it says there could be negative minutes on site, and we know people can't spend negative amount of time on a website. It turns out this isn't going to matter that much. And all I'm really trying to capture with my prior is that, I don't know, it's some number between minus 200 and 200 and kind of, I really think it's probably closer to the 5 or 10 minutes, because unless it's like Netflix, people don't spend that much time on websites. So I'm trying to kind of capture those beliefs. You could do it more properly and have a prior that actually didn't have negative values, but it turns out it's not going to matter. So those are my priors. And I take, basically Bayesian inference has a formula in it called Bayes' rule, that tells you exactly how you should update your beliefs after you see some data. So that's the whole idea. You have some prior distribution, and then there's some algebra that happens, and you update your beliefs. Sometimes you can't do algebra, you have to write a computer program. But the really basic concept is that you have this prior, and then the Bayesian inference, the Bayes rule, tells you exactly how you should update that after you've seen some data. And that's actually also all easier to see. I'll show you the math in a second, but the idea is actually much easier to see in a picture. So this is the posterior that I computed using Bayes' rule. And this blue line is my posterior beliefs about the range of values that the average time on site might take for A. Now, importantly, this isn't the range of time people who see A might spend, because some of them probably spend 0, some of them spend more than 5 minutes. This is the range of values that I think the average could be. So I think the average could be somewhere between 5 and 5.6. And the red line is showing you what I think the average might be for B. And they're super overlapping. That's a technical term, super overlapping. And I was trying to make a joke there, but I can't hear you laugh. So I'm feeling kind of left out in the cold here, but that's okay. We'll press on. The idea here is that the distribution is very overlapping. So it's kind of telling us, well, we're not very sure that B is better than A. It might be better than A, but then again, there's all this distribution here of A. So it could be that A is better. We're not really sure based on the amount of data that we have. If you want to know how that works in math, the part I skipped in the pictures is you have to have some kind of mathematical model for how the data, the time on site for an individual person is generated. And I'm going to also assume that that is normally distributed with whatever the average is for the group and a variance S. So S is kind of how much noise we have from one person to the next person. So if I assume that that's true and I do some algebra behind the scenes, it tells me that the mean time on site for the group, given some data that I've observed, is going to be a normal distribution with the average of whatever the average of the data is, and then this variance, which is, you can see if I have a big N, that variance is going to be smaller. There's a whole lot of algebra you have to do in your head because there was an inverse there. I'm not going to get into that. I'm just going to skip all the derivation stuff, and I hope you don't mind. But this is, if you want to read more about it, you could read about it like on the Wikipedia page for the normal model.
Well, before you move forward, there were a few questions.
Yeah.
Did you say that the distributions become uniform at any point because someone asked about it?
I don't, if I did, that was a mistake. There are no uniform distributions here. There's
yeah, it's
just
all normal. Yeah.
Normal distributions.
And yeah, the question was again about the time spent and why do you assume? So I just wanna add, if you move to the next slide, in the end we care about the average of the time spent or the average of the amount spent, etc. So even if the distribution underlying the data is not normal, the averages, once you have a large enough sample, becomes very, very similar to a normal distribution. So whatever prior you're going to put on it, assuming it's diffuse enough, it all converges very quickly with data to look like a normal, which is why it really doesn't really dramatically matter.
Yeah, so we're using normals here, and if you had very small sample sizes and very, very large noise, then you might not be in a regime where the normals make sense as approximations, but here they definitely do. In fact, Ron and I argued about how thin the data had to get before the normals made sense for about 6 months. And we convinced ourselves numerically that, like, for data of any kind of reasonable size, like if you had 10 visitors to each version, then you should start worrying about things not being normal. All right, for those of you who don't like math, I have one more slide. It's the same exact math, but in code. So if I wanna compute so I'm gonna compute 2 things here. The posterior mean, which is if I had to make my best guess of what the average time on site is for the group, what should that be? And then this posterior standard deviation, which is how sure am I about what that average is. And so I'm just gonna add up the sample size in each group, NA and NB, I have to get this S, which is basically how noisy the time on site data is. So that's just our noise calculation. And then the posterior mean of A is just the average of the data. That's the same thing back here on the previous slide. Well, for some reason I can't go back. It's just this Y bar. And then here is in code what that posterior standard deviation. So this is what's my best guess, posterior mean, and the posterior standard deviation is how sure am I about that guess. And once I've done that math, what I can do is I can actually compute intervals. So a lot of you like confidence intervals. And so we can compute a thing called a credible interval, which is like the Bayesian version of a confidence interval. And literally what we do, let me just go back here, is if we want the credible interval for B, we just chop off the tails of B. The 2.5% on either side will give us the 95% credible interval. And so it's going to be something like 5.3 to 5.55 or something like that. So to actually compute that in R, I'm going to use this function called qnorm. So qnorm just gives me the cutoffs. It's like looking up z-scores in the back of your statistics textbook. It's kind of the modern version of that for people who are older like me. So qnorm, and then you just say what range you want. So I want the 2.5 percentile to the 97.5th percentile for a normal distribution with the mean posterior mean A and the standard deviation posterior standard deviation A. And I get for A, it's 5.13 to 5.51. And I can do the exact same thing for B, and I get that its credible interval is 5.18 to 5.55. So we're getting this kind of idea that, oh, these intervals overlap. So there's lots of potential scenarios in the world where A is actually bigger than B on average. And we just haven't gotten enough data to see that. So none of this is actually comparing A to B. So let's talk a little bit about that. We have the posterior distribution for A and the posterior distribution for B, but we can also use Bayesian inference to compute the posterior for the difference between A and B. So that distribution tells me how much bigger is B than A, or A than B, when I compare their means. So I can actually compute that posterior distribution, which is drawn here in black. And so I drew a vertical line at 0 because the way we interpret this is the range of values where B has a higher mean time on site, and the left-hand side is the range of values where A has a higher mean time on site. And so you can kind of like look at all this area here, and all of that area would be the probability that B is bigger than A. Does that make sense?
Ellie, before we just move forward, there was a question about S squared. What is known in the model and what is not known in the model?
We're going to assume that S is known. There are versions of this where we assume that S is unknown, but for large sample sizes, it's pretty reasonable to do what I did here, which is I just compute S directly from the data. It turns out that if you assume that S is unknown, then we would have to run an MCMC sampler to actually fit this model. And this just makes it a little bit easier because everything is actually just formulas. It's really fast. But you can do the version where the S is unknown. Anything else, Ron?
No, someone just said that you never want to run MCMC.
Well, we're going to run some MCMC a little later. Yes. Yes. I like running MCMC, but not everybody does. I can feel for those who don't. All right, so I have that distribution. That actually, it turns out that if the distribution of A is normal and the distribution of the posterior for B is normal, then the difference between two independent normals is also normal. This is the normal is just a magical distribution. It has a lot of nice properties. And so I can actually compute the posterior mean and the posterior standard deviation of the difference using this code that's right here. And this is like literally something you can just look up if you Google the difference between two normals, which every time I write code for this, I Google what's the formula for the difference between two normals. You think I would learn it after 3 years, but I haven't. Or you can look at these slides and see. So it's just, you take the posterior standard deviations for the A and the B, you square them, and then you take the square root. So once I have those computed, I can use this little formula here where I have 1 minus P norm. This is actually computing the probability that the difference is greater than 0, meaning that B is bigger. And so this number right here, this 0.631 is the probability that the B version produces a longer time on site on average. And then, so that's the end. That's where Bayesian analysis ends. We have this really nice probability. It's just, you know, if you believe my priors and if you believe the assumptions I've made about the model, then 63.1% is the chance that B is better than A. And you can just leave that in the hands of a decision maker to decide whether or not they want to use B versus A, or maybe they want to run the test a little bit longer because that doesn't seem like a sure enough answer, and that's perfectly fine to do within the Bayesian framework. One thing I wanted to sort of pause to mention here is that last time when I did the hypothesis testing, I was using all these built-in functions in R, like t-test and you know, power t-test and all these built-in functions that made it easy. Here for the Bayesian analysis, I'm kind of doing a lot of stuff by hand. And the reason I did that is there's just not really a great package that sort of packages up all this stuff. And I also wanted to kind of show you how it works under the hood a little bit. But if you're ever trying to apply this code and you kind of get stuck or confused, feel free to shoot me an email, because I understand that it can get confusing because we don't have those nice packaged up packages. I think that's it. Let me just check my notes. Yeah, that's where I am. Oops. All right. So last thing on the analysis side, and then we'll jump into the planning, which is where the fun stuff happens. So a lot of people get hung up on the priors, and I'm here to say, just don't. As you get more data, the posterior becomes more and more influenced by the data. So if you have any kind of reasonable amount of data, and in most practical situations where you do A/B testing, we have sample sizes that's usually in the hundreds, because these are done in digital marketing spaces where you have plenty of customers. It's easy to randomize, it's easy to collect the data. This isn't like lab science where you might have a sample size of 10. So in most practical marketing situations, you have enough data that the priors are not going to affect the analysis very much. And as we kind of hinted at, even the model doesn't affect the analysis very much when, if you have a sufficient amount of data. Another actually way to sort of spin priors as a positive is that if you have prior information, like if you know something about what typical times on site are for your website, the priors are a very principled way to bring it in, and there's no way within the frequentist framework to bring in that prior information that you want to kind of impose on the analysis. So priors can be used to kind of regularize things, to say, okay, when I see a really extreme outlier, that isn't consistent with what I know about the system, my priors are gonna kind of tamp that down and say that must be kind of odd, you know, that's an odd outcome. And priors are a nice principled way to do that. The third thing about priors that you should know is they're very useful when you're planning an A/B test. So when you're planning an A/B test, it's actually very handy to know something about how things might turn out, because there's different ways the test could go, and by knowing how they might turn out and what outcomes are more likely than other outcomes can help you with planning the test. And so we're going to actually leverage the priors in planning an A/B test just here in a few minutes.
Before you move forward, the question that kind of repeats a little bit, okay, you said reasonable amount of data to define the prior. How do you know it's reasonable? How much do you need? Like, how do you know your prior is a good prior?
I guess the best thing to do is to, you probably shouldn't, you should do what I say, not what I just did, which is you really should just use a prior that reflects your true prior beliefs. I have a whole chapter.
You will show an example, right? You will show an example later, right?
An example of
how we came up in our paper with priors, right?
Yes, we will show you a principled way to come up with priors. Yeah, absolutely.
Yeah.
Uh-oh, the MCMC people need a different meetup. Okay. Well, Ron and I have another paper that does a lot of MCMC, so our ladies can invite us back like a year from now when we're done that project.
And we'll have to present.
It'll be all MCMC all the time.
So someone is being driven crazy by test and roll. Is there a reference behind it? So we can say where the name came from, right? It's not like a secret.
Yeah, go for it, Ron.
Yeah. So we visited a company. And the company told us, oh, we have these experiments. We just want to run them quickly and enroll them. So we just call them test and rolls. And we're thinking, we're just working on this project. And we're like, oh, this is exactly what we're advocating for everyone to do. So this is where it's coming from. It's just a rollout of the test.
And it was a retailer who does test and roll primarily during holiday season. Like, it's Black Friday, so we're not really sure what the homepage should be on Black Friday, but we are not going to run the test later than 10 a.m. because by 10 a.m. we want to roll.
Yeah.
We want
to
deploy
really
and kind of get things, because the other thing is the test can kind of slow down the website, so you don't want to leave those things hanging there forever. You want to get the website, especially on Black Friday, you want to pull parts of the website that might be computationally heavy out and get the, let's roll, let's start sucking in money as marketers do. Other questions, Ron?
Nope.
Okay. Oh, the one last thing on priors. Hopefully you guys, I guess we have a lot of Bayesian, so people aren't stuck on priors. That's good. Oh, there's a typo. The prior we just used. That's a bad typo.
No, just the prior we used. The J is just, you don't need it. Okay.
So the prior we just used is actually drawn on this picture. It's the gray line, and you can see, visually it's very flat in the region where the posteriors actually ended up, and that kind of flat prior is basically not influencing what the posteriors are very much in that range. Oh, and I had another slide on priors. Are we done with priors?
I think we're done. But...
Oh, no, I have to do this one because it's important. It's going to be important later.
Yeah.
So in this analysis, I used the same prior for A and B because I know nothing about A and B. Really importantly, that doesn't mean that I think that A and B are the same. It means I am not sure about A and B, and I'm not sure about them in the same way. So the priors reflect our uncertainty about A and B, and because we're uncertain, even though my best guess for A and B in the prior going in is that they both have the same best guess, there's a wide range. And so A could be better than B, or B could be better than A. That's all I have on that. All right, so just to summarize, here is how to analyze an A/B test using Bayesian analysis. You pick treatments and an outcome measure. You randomly assign A and B to some users and you record the outcomes. 2 is surprisingly easy to mess up. I've seen people who run websites mess that up many times. The third step is that you quantify your beliefs about the outcome with some kind of prior distribution, which I've tried to convince you is not going to be too important in practice. Then you update your beliefs according to Bayes' rule to get the posterior distribution. And then you draw pictures of that, or you compute intervals, or you compute the probability that B is better than A. And then you make a decision, or you can go back to 3. So there's nothing about the Bayesian setup that prohibits you from collecting more data. In fact, if you collect a sample of 500, update, and then collect another sample of 500 and update again, you will get exactly the same answer as if you had collected 1,000 and updated. So it's kind of, a lot of people in business really like this property, because the idea that I have to plan my sample size and then, you know, run the test and not like stop before, you know, if I see significance, I shouldn't stop. Ron has a whole paper on that. So if I see significance in an A/B test using a hypothesis testing, I shouldn't stop. But in the Bayesian framework, you can do whatever you want. You can stop now, keep going, whatever. You're going to get the same answer either way. So that's kind of a nice property of that. So I guess everyone's found the questions document. I wanted to remind people that they should, if you have questions, you should put them in the questions document. Are there any other ones? Or this is going pretty smoothly with interrupting me for questions.
Excellent. So there is a question which I think about something you said, which I didn't listen to very carefully, but the question, I guess, is how the stopping rule affects, I guess, like you said, you can always stop in a Bayesian experiment, but then when you stop might affect your type 1 or type 2 error, right? Like, do you make mistakes about which arm is better or not, right?
Yes, it could affect your type 1 and type 2 error.
Yes, but what I wanted to add, I haven't answered the question yet, will show you that that's not the point of a test and roll. So that's...
Yes, in a test and roll, you're going to test and then roll, and we won't worry too much about dynamic stopping. All right. So now we get to the part where we talk about test and roll. So this was all inspired by seeing a screen that looked like this. So this is a typical A/B testing screen for email. So it says, select the size of your test group. We'll send version A and B to a random sample of recipients and then send the winning version to everyone else. So what's going to happen here is they're going to send A and B to 8,910 people each. This is an email tool, so we can just blast those out. And then we're going to wait 7 hours. And we're going to see how many people open the A email and how many people open the B email. And then the tool will actually automatically pick the one that got opened more and send that to the rest of the people on the list. So we have to make a decision as a marketer. We have to kind of move this slider and decide how many people should get A and how many people should get B. And so I would often have students come to me and say, where do I set the slider? And I was like telling them to go figure out the sample size for a hypothesis test, and really funky things happen when you do that. Like it could be more, the hypothesis test could require more emails than you actually have email addresses in your database. And then what should you do? And it kind of seems dumb to send the test to everybody, because then I never get to use the winning version, especially if we think of this test as kind of a self-contained thing, like we're doing the subject line on the Christmas email and we're only going to do that subject line once. So that was kind of the motivation behind this. And it turns out that that is a decision problem. So let me kind of formalize that a little bit. So in the test phase, you choose N1 and N2 customers to send the treatment, and then you send them out and you collect data on how much profit you're getting for both of the treatments. And so now I'm going to start talking about the outcome is profit. That's kind of important to the setup. You want that outcome to be profit or proportional to profit. So that's the test stage. Then in the roll stage, you pick a treatment to deploy to the remaining N minus N1 minus N2 customers. So there's two decisions. First, how many people do I send the treatments out to in the test? Then when the test is over, which one do I deploy to the remainder of the population? And my goal, well, this is the important thing. This is kind of the core insight. Why are we doing this? Are we doing this to minimize type 1 error, Ron?
Or are we doing what?
Oh, sorry, I caught you off guard.
Oh, I'm like answering questions here, like in chat. I cannot.
Okay, go back to the chat. Go back to the chat.
No, that's fine.
It's a rhetorical question, and I was just looking for someone to engage with. So why are we running the test? Are we running the test to minimize type 2 error? No, not really.
No.
Are we running the test to minimize type 1 error? No. I'm running the test because I want to make more money. This is the, you know, the insight that being a business school professor will bring you. The goal is to maximize the profit, and I want to maximize the profit actually over the whole thing. So when I send out these emails to A and B, I make money. And then when I send the winning version, I make some more money. And I want to make the most money I can from all of those emails that I'm going to send out. And so my goal is to maximize the profit for both stages. So then Ron and I sat down for a while and we have this N1 and N2. So we're trying to figure out what should N1 and N2 be. And I wrote a computer program to try to optimize that. And then Ron did a lot of algebra, and it turns out that the optimal sample size is this thing right here, this thing with the radical and all this stuff. Let me give you the background assumptions that we're making. So we're assuming it's actually the same setup I showed you before when we were analyzing a test. We're going to assume that the profit earned for each customer is normally distributed with a mean for each group and a variance S, and we're going to assume that S is known. And then your priors are that those M1 and M2, found another typo. So that should say M2 there. So both M1 and M2 are normally distributed with a mean mu and a standard deviation sigma. So I make those assumptions, and then I do a bunch. I can actually write down a formula for the total profit I earn in the test stage and the roll stage. There's a bunch of integrals. I have to take those integrals. And then you keep doing all that. And there's like 5 pages at the back of the paper. And you end up with this nice closed form formula. So that's kind of the core result methodologically in the paper, is that we provide you with that sample size formula. Which you could code up in R, but there's no need because I coded it up for you. So these functions are all in a file called nnfunctions.r. So if you source that file, then all of those functions will be loaded for you. And that file doesn't do anything, it just has the functions that I'm going to use. And in there, there's this function called test size nn, and you pass it in. N, which is how many customers you have total to play with, like on your email list. Your S, which is the noise in the response. Your mu, which is your best guess at what the average response will be for both of your treatments. And sigma, which is like how sure are you about the range of likely responses for your treatment. So I've put in let's see, 100,000 for N, 0.68 for mu, 0.03 for sigma. And then this is a case where we're going to think of the data as being binomial data, like zeros and ones, but we're going to approximate it with a normal. And so you can actually estimate S as mu times 1 minus mu. So that's a little trick. So then if I call this test size NN, I get that you should do 1,108 customers in the A group and 1,108 customers in the B group. Does that all make sense? This is it. Now you know how to test it. This is like the core thing. Are there questions, Ron?
So there are a few questions about the population size, like, you know, what happens if you don't know it in advance, or it just comes dynamically into your website? So what do you do with that?
So this really was motivated by email and catalog, and like that retailer that came up with the name for us is doing email and catalog where they know how big the list is. In a website, you wouldn't know, but you typically know how much traffic your website's going to get, say, in the next, say you know that you're going to change the homepage every 3 months. Then you could look at how many people are going to come to the homepage in the next 3 months. And I want to run the test for kind of the optimal amount of time so that I still have time to deploy the better treatment and earn some profit against that better treatment in the later stages of things. So you would have to estimate that. There actually is, I have linked at the end, a version of this. So while we were working on this, somebody else, his name's Chris Syed, he works at Stitch Fix, kind of came up with the same idea independently. And I have a link to his blog post at the end. He looks at it as a discounting problem, which actually has some advantages if you don't really know what that N is. But if you have like an email or a catalog case, then you would know what that N was, which was kind of our motivation.
The other question was a little bit about the symmetric assumptions. Is it like, does this formula require symmetric priors? And also, does it help work? So this is about symmetric prior, but also, can you allow for asymmetric sample sizes if you want to be risk averse or something like that?
Absolutely. So I have that in the, let's hold off on the asymmetrics. We'll get there. We'll get there. It turns out that you can't get a closed form formula, but you can write a computer program. And it turns out that this test size function, you can actually pass a vector in for mu and sigma of 2 values each for mu and sigma, which are for your, if you have asymmetric priors. And I'll show you that at the end. And if you didn't follow that, I'll also show you, I need to speed up, I guess, is my vibe here. Do you think the question suggests we should speed up a little bit?
I think you can move forward, and then okay. At worst thing, we'll go back to answering questions.
Yeah, we'll get there, we'll get there. All right, so you might be wondering, like, well, why is this the profit maximizing test size? So there's a function called test eval nn that's also in that file that you sourced. And that actually spits out a bunch of information about a test with a given test size. So I'm gonna take my test size function and assign that to n star. So that's my optimal test size. And then I'll run this test eval function so I can see how well it does. And it gives me a bunch of stuff. But the important things here are the profit. So that's the total profit. It's 69,617. So the total profit of this test enroll is 69,617. And it also gives me the error rate. So that is how often I deployed the wrong treatment. And I'm going to be deploying the wrong treatment 68% of the, or 6.8% of the time. Now, I didn't set that. The formula decided that this was the profit maximizing sample size, and it turns out, it just happens to be that the profit maximizing sample size produces an error rate of 6.8. Now, this is not a type 1 error, it's not a type 1-2 error, it's a deployment error. So it's that you sent A when B was the better treatment or vice versa. And we think it's kind of cool that it'll just figure out what is the optimal error rate for you, but you can kind of look at that if you're interested. I'll skip everything else that's in that function. But here what I'm doing is I'm going to run that function against a bigger sample size, and I get a profit of 69,350, which is less than 69,617. And here I run it for a tiny test. Let's say we just ran 100 in each group, and the profit would be 69,367, which is less than 69,617. So you can see that both of those are worse. So literally, we've just done a bunch of algebra that finds the thing that makes the highest profit. And maybe it would be easier to see that in a picture. So I just ran that function a bunch of times for different sizes of tests. And so 0 would be, I don't run a test, I just deploy randomly. I just pick one. 50,000, so our capital N was 100,000. So 50,000 means I basically use the entire population for the test, which actually turns out a priori to be the same as choosing randomly. I'm just going to send half, send one version to half the people and the other version to the other half people. And in expectation, that turns out to be the same. And everything in between. And you can see that that optimal sample size is right here. So there's a couple kind of cool things about this plot. First, you can see that as you start to get a bigger and bigger test size, your profit goes up like kind of astronomically. So it actually is very sensible to run a test that's small, because even if you can only run a tiny test, you're still ramping up that profit curve really fast. So you might as well run that small test. And then the profit kind of trails off as you get to a test that's too big, but much more slowly. So if you're unsure of anything, you might run a test that's like a little bit bigger. You won't deteriorate profit too much. And we can also plot the error rate. Remember, I showed you that error rate in the output. So I just ran a loop over a bunch of values, and I'm plotting a picture of what the error rate is. And you can see that the error rates, of course, it would be 0.5 if I just chose randomly. I'm gonna half the time get the right one by luck. And then it, as I do that bigger test, my error rate goes kind of way down until I get to sort of the optimal error rate. So what that function, that test size NN function is doing is it's making the optimal trade-off between the opportunity cost of the test. So during the test, you're sending the wrong treatment to kind of half of your customers by default. And so you don't want to run the test too long because you know that you're sending the wrong treatment to half the customers during the test, but you want to trade that off against the risk that you deploy the wrong treatment. So you send the wrong treatment to the customer, then you make a lot less profit. And so the test size NN is actually making that trade-off optimally. And kind of one of the most important things about it, when you do sample size planning for hypothesis testing, you kind of pick what is the smallest effect size that you'd like to be able to see. So you just have that one value. Whereas in this approach, we have a prior over all of the likely, all of the possible differences between A and B. So our priors on A and B define a prior on all of the likely differences between A and B. And what this trade-off actually recognizes is that when you make mistakes, they're actually very small mistakes. So if A and B are really close, it kind of doesn't matter as much which one you pick, right? You don't lose as much profit by picking the wrong one. And what you really want to do is run a smaller test size and pick up on the really big differences and make sure that you deploy the right one when the difference is very big. Is that landing, Ron? That idea?
Asking me questions while I'm typing.
Oh, sorry.
That's fine.
You always explain this idea of finding the big tests much better than I do.
So the idea is, like, if you know what are type 1 and type 2 errors, type 1 error says if there's no difference, I really don't want to say what there is a difference. But actually, if there's no difference, you don't really care about selecting A or B, right? They're really close. When you care about finding the differences is when A and B are really different. And the chance of making a mistake there by just looking at averages is really small. So if you get like 1% and 99% conversion rates, you will need a really bizarre experimental result to tell you, oh, I think they're the opposite. But if you have 1% and 1.000001%, you don't really care about deploying 1% versus 1.00001 because the difference over the population is pretty small. So that's kind of, this is why I bring it back to type 1 and type 2 error. Type 1 and type 2 error really want to say directions. Is it bigger or smaller? But you actually want to say, I only care if it's bigger when it's really big, and I don't really care if it's bigger when it's really close to the other one. Make sense? I hope I answered the question.
Online is always a little bit weird because you're not sure. Thank you for clapping, Chun. I appreciate it. All right, so we went over that function. I just had some values of mu and sigma and s in there. But let's actually talk about how you would pick n and mu and sigma and s. So n, what is n? N is the number of customers you have available. We talked a little bit about how you might set that if you had a web page. Typically, it's like the number of people you have available to do the test on. And I won't go through the code, but the code just makes this little plot, which shows you, so what if I had a bigger population versus a smaller population? And the cool thing here is that when you have a bigger N, you end up with a bigger test. So if you are a small advertiser, you should run a small test and then try to use that information quickly. And if you have a very large population, like your Facebook or Google or something, you should run a very large test and then deploy that on your very large remaining population. And I always liked this feature because this solves the problem that I have students who run tests as part of projects. They run the typical power t-test calculation that we talked about in the last session. It tells them that they need a sample size that's bigger than they could ever possibly get. What do I do, prof? And there really was no good answer to that. I'd always say, well, just run the test because you need to get a grade. But that was a very unsatisfying answer. And so now I actually, I had a student who was running an email newsletter on 20,000 customers total that they had on their email list. And he actually ran it as a test enroll for his class project. So that's N. N is easy. Mu is also easy. So mu is the average profit that you expect across the treatments that you might test. So let's see, I'm gonna do the same little trick where I vary mu to make a plot. I won't go through that code. You can see from the picture that it doesn't matter what mu is. When mu is the same for A and B, it doesn't matter at all. It doesn't affect what the sample size is. So the sample size stays the same no matter what mu is. Now, if mu is different for A and B, which that function can accept, I mentioned, I'll show you an example later, then it matters. So, but it doesn't matter in this case where A and B are the same. So that's mu. What's S? S is the how variable is the profit from one customer to another. So it's the standard deviation in profit within a group across the customers in that group. So that's like noise, right? That's like how much noise, if I think about this in terms of a test, it's if I run 500 customers, how much like just noise is there going to be in that data? And so when the noise is bigger, I need a bigger test because it's actually optimal. Even though I only have 100,000 customers, when there's more noise in the data, it's worth it to sort of blow some of those customers in the test. That did not come out right at all. And then it's worth it to do a bigger test to get a better signal from that test so that you can deploy the right thing. And of course, if you have like very little noise, you can get away with a tiny test because all you need is a tiny test because you're going to get a very clear signal from the data that you get in that test. And down here at the bottom, I have this note. Hypothesis testing requires much bigger sample sizes. I don't know if any of you remember the sample size formula, but the traditional sample size formula has an S squared in it instead of an S, which means that it grows much faster with S than this sample size formula, which is basically linear in S. And so that's another kind of advantage of this is that the sample sizes are going to be much smaller and they're more profitable. So who wouldn't want a smaller test that's more profitable? And last, what is sigma? So sigma technically is the prior variance or the prior uncertainty it's the standard deviation, sorry. So it's the prior uncertainty in what the average is for A and what the average is for B. And that actually defines a prior on what the treatment effect might be. So treatment effect in A/B testing just means the difference between A and B. So if I take the absolute difference between the average performance for B and the average performance for A, or 1 and 2, they're labeled here, then I can actually plot the prior distribution that's defined by sigma. And that's like a half normal distribution. So when sigma is big, it means there's a bigger chance that A and B are very different from one another. And when sigma is small, it means that A and B they're defined by their priors, the priors are tight, and so A and B are pretty close together. Let me say that again. When sigma is big, it means that A and B are on average going to be very far apart. And when sigma is small, it means that A and B are on average going to be very close together. So here's a plot of the sample size. So when sigma is bigger, there's a bigger difference between A and B, and we can get away with a smaller test. Remember, Ron said when A and B are quite different, like a very small test will get you the right answer because you'll see it right away. Like it'll be very clear in the averages that these A and B are very different. So when you have a bigger sigma, you can actually get away with a smaller test. So that means you really need to think carefully about what sigma should be. Does that make sense? This is a good time to pause because I've kind of gone through all the inputs, the N, the mu, the S, the sigma, and I've basically come to the conclusion that when we really need to think carefully about what are mu and sigma because they have a big effect on what the optimal sample size is. So we're going to have to think carefully about that. Are there questions, Ron?
So there are questions, but they're more, so there was exactly this question of what is the mu and sigma and what they represent, which I think you've answered. They just asked like, I don't know, 15 minutes ago.
Yeah.
There is a question slightly more generic. So suppose there's an A, B, and C test or A, B, C, and D. How do you apply this method or what would you do?
Do you have an answer?
Well, you need to write down the profit function, which is a kind of a long integral, and just numerically optimize it, right? So you can write it and plug it into software that will give you an output, but it's not going to be possible to use like our nice formula because it's not going to have a closed form. And then I thought it's actually probably a good idea to have it in the package.
Yeah, that's what I'm thinking.
Exactly.
Well, thank you, our ladies, for adding to our to-do list.
So
yeah, no, that's definitely a good idea. I have to look at the function. If anyone's like really super advanced in R, take a look at that function and see if it already does it. I don't think it does.
No, I don't think ours does. I think we only.
I don't think so, but we should check that.
And the other question was, are you gonna cover multi-round bandits and reinforcement learning, or you didn't?
Oh boy, if we would be here till 10 o'clock.
No. Just comparing to it, not like.
No, I didn't put that in.
So there was.
Paper, though.
So there was a question, why do you do it in 2 steps, like one blast of a test and then a roll, and not like incrementally smaller sample sizes and learn and then optimize as it goes?
So yes, do you want to answer that, or did
so
you already?
I answered in chat, but the idea here is we're doing a restricted version of it. We're going to learn in one stage and do that, and it gives you 2 benefits. So the first one is that for some tests you just can't do it piecemeal. Like you do email and people click so little that you need to wait 3 hours every time. If you send 100 emails, you need to wait 3 hours, another 3 hours, another 3 hours, you run out of the day. So for some tests, you just can't do it in smaller samples. You need a big chunk of people to get any data back quickly enough. And the other thing, and this is what Ellie's not going to cover, but we spent a lot of time on it in the paper, immediately we get this question of, oh, we have this optimal method, which reinforcement learning or multi-arm bandits, they kind of find the optimal solution dynamically. And we were able to prove that we're getting pretty close to it. How close? It's so close, it's hard to see in a graph close. And we ran a lot of simulations, a lot of tests.
It's close in terms of profit. It's
yes, the profit.
Almost as profitable to do it in a test and roll as to do a more dynamic algorithm.
Yeah, so dynamic one is more profitable, but in a tiny difference. And we tried different priors, we tried different number of arms, we tried many, many other things. And it worked well.
If you have a lot of arms, like dozens of different treatments you want to try, that is one place where the dynamic algorithms have a bit of an advantage.
Which, by the way, means that we probably solved the multi-armed problem, because then how did we calculate the sample size? So it probably is in the code somehow.
Oh, yeah, it is. It must
is
be. We must have implemented that.
Okay, so we should put it in the package.
Yeah. We need to, nothing's documented yet.
Yeah.
I apologize. Yeah, and the reason I left that stuff out was this workshop was supposed to be on how to test and roll. So it's not why you should test and roll or why test and roll is better than multi-arm bandits. If you want to know about that, you should read the paper. But I wanted to focus tonight on, like, if you actually want to do this, what are the things that you really need to know? But those are all great questions. All right, so how to come up with S and sigma for your own test. And I forget, who was it that wants MCMC? I forget her name. She posted on my LinkedIn too, Alexandra. So Alexandra, we're getting to the MCMC finally. Here we go. Sorry, I get off of, somehow I make my slides not the active window and then I can't page down. All right, so imagine you are in a world where you have some previous A/B tests that kind of represent the range of things you've tested in the past and kind of the range of things you might expect from the treatments that you are planning. So here's the data. It's in this data frame called EXPTS. And this is the first test. And in the first test, A had a conversion rate of 0.37 and B had a conversion rate of 0.323. And in the second test, it was 0.40 and 0.46. So B was the winner there, and so forth. So imagine you have data like that. Actually, Ron has data like that from a major A/B website testing platform.
You can say where this is from, so it's in the paper, right?
It doesn't say where it's from in the paper.
In the other paper, it does. So.
Oh, okay. Anyway, it's from. Can I say it?
Yeah, you can.
It's from Optimizely, which is a major website A/B testing platform. We have a data set of over 2,000. By we I mean Ron has a data set of over 2,000 website A/B tests that were run by different website testers. So it's pretty representative of the kind of tests that people run. And the conversion rate is whether or not you clicked anywhere on the page, because you need to have something that's comparable across the different tests. So this is synthetic data, but it's actually simulated to be very similar to that real data that we have. And so imagine you had that data. So the idea we had was you could meta-analyze those past experiments to figure out what mu and sigma should be. So if we assume that that data represents the range of performance that we might see in a future website A/B test that we're planning, we can fit a model to that data to estimate mu and sigma for these types of tests. And we're going to use Stan, which is a flexible open source tool for Bayesian modeling. And you can access Stan by installing the RStan package. Stan is a multi-platform package, so you can access it from Julia or Python or the command line, but we'll use RStan. So when you use Stan, you have to, so I'm going to, let me back up, make sure everything's clear. I'm going to take this data from previous A/B tests, I'm going to fit a model to that data that's going to tell me what mu and sigma should be for some future test, and that I'm trying to plan. So I'm trying to plan a test enroll, and I want to know what sigma is likely to be. So when you use Stan, you have to actually write down, using Stan syntax, a model. And I don't have enough time to I wasn't planning to kind of teach everybody the Stan syntax, but I can kind of show you the important pieces of it. So this piece down here labeled likelihood is where the model is defined. And what I'm doing is I'm saying that for every test, there's a TI. That's kind of like, it's where the test is centered. So if this is on a home page, people are more likely to click than if it's on some page deep down in the site, and so that's T. Then the two treatments, M1 and M2, both have their own means. So that's this M1 has its mean, has its mean response rate that's centered around the T. So T is kind of the center for the test, and then M is the center for the treatment within the test. And if you had more treatments, there could be 3 or 4 or whatever. And then I say, okay, the actual response that I get from a customer in group 1 is normal with mean M1 and this variance. And this variance is that way, for those of you who are like really into modeling, that variance is that way because I only have the aggregated data. And then the other Y. So this Y is not actually the observation for an individual, it's the average for the test. Anyway, if you didn't follow the last, while I was explaining those 5 lines of Stan code, not a huge deal. To run the model, you just run this sampling statement, and that is actually running MCMC. So just all you need to know to drive MCMC is it doesn't give you a formula for the posterior of something, it gives you random draws from the posterior. So then you can just plot a histogram of those random draws if you want to see what the posterior looks like. Then I'm going to run summary, which gives me this output that actually looks a lot like regular regression output. And I'm really interested in the sigma and the mu, which are the sigma and mu I want to use to run my future test. And so I get that mu is 0.68 and sigma is 0.0285. So I run that meta-analysis of all the previous experiments. And what it's telling me is that across all of those experiments, on average, the response rate is 0.68. And the variance around that is about 2.68. So it means we're going to see typical effect sizes in the range of 4%. So we might see a conversion rate of 64 versus 68 would be kind of the typical A/B test in the data. But then now we have that number and we can use it to plan a future test enroll. So I'm gonna pass those numbers. I actually had to literally type them because I was, whoa, what happened? I went the wrong way. Sorry, I just went the wrong way on my slides. So I actually took these numbers and I typed them in and computed my optimal sample size, and my optimal sample size is 1144. And I can run test eval, and it tells me what my total profit is going to be and what my error rate is going to be and all that good stuff. So that's how I would plan a test enroll. So, and then to finish up the process, you're going to go out in the world and you're going to actually run the test and get the data. And so I have a data set that's kind of the hypothetical data set we're getting from the test. And you can see the average. Actually, before I jump into this, let me pause there and look at Ron to see if Ron has any questions.
Nope. I think
nope. Okay, good.
Yep.
So we run the test. Now we ran the test. We ran the optimal sample size of 1272. And we see that the A version had a 52% conversion rate and the B version had a 50.5% conversion rate. So it looks like A is better. So now we have to decide what to do. So now we're back to the analysis stage that we started with at the beginning. So I can compute posteriors for each group. So there's what the posteriors look like. So for this particular test, we're getting a little bit more separation between A and B. So it looks like A, pretty good chance that A is better than B. So how do we decide what to roll? Well, the posterior mean is our best guess at how well the treatment will perform. And it turns out that expected profit is maximized when you choose the treatment with the highest posterior mean. So, and that's just a general rule for decision theory. So expected profit is maximized when you choose the treatment with the higher posterior mean. Like you can look at a book on decision theory like Berger. So we just need to pick the one that has the highest posterior mean. But how did we compute the posterior mean? That's just the average for the group. So that's the average in A. Sorry for my not tidy. I spent an hour yesterday thinking about how to do that tidy, but well, it wasn't an hour, 5 minutes, and then I gave up. So I did it the old-fashioned way. So I'm just taking the test data, taking all the people in group B, taking their profit, and averaging them. So you could actually totally skip the Bayesian analysis and just compute the average profit for each group and deploy the treatment with the higher profit. Like you don't actually need to know how to do the Bayesian. Now you need to do the MCMC analysis to get the priors from the meta-analysis in order to plan the test and roll, but you don't have to, once you do the test and roll, you just pick the one with the higher average and then you roll. And that's why we liked the name test and roll so well when it was proposed to us, because it really is like, we're not going to do a lot of analysis, we're just gonna pick the one that has the highest average posterior mean. All right. So just to summarize that all up, because it took us a long way to get here, I like easy step-by-step how-tos. So step 1, come up with priors for your test. So if you have data on any past treatments that are similar to the ones that you plan to test, you're gonna fit a hierarchical model to that data. And so I'm just repeating the code that I showed you before, where I run the hierarchical model and then I summarize it to get my sigma and my mu. And this data doesn't have to be A/B tests. So for instance, if you were an email marketer and you have a bunch of past tests that, or sorry, past campaigns, you've sent a bunch of emails prior, you could actually just do the meta-analysis on those and say, well, I think my treatments are likely to be in the range of response that I've gotten on past email campaigns. And I've actually done that. I really wish that MailChimp would implement that, because it would be very easy. They already have the data on how the past campaigns performed. So since they already have that data, they could just build it into the tool, and they, instead of giving you that freaking slider that nobody knows what to do with, could actually set the slider to what the optimal level is. So if you know of anyone at Constant Contact or MailChimp, please put me in touch, because I will make an impassioned plea that they should implement this. So that's step 1. Step 2, you use the priors to compute your sample size. So we use that test size NN function that I wrote, and you pass in what you got out of your meta-analysis, and you can run test eval NN if you want to see kind of what your expected profit is for the test and roll and what your error rate is. And you know, there could be, here the error rate is 7.3%. That means 7.3% of the time you're going to deploy the wrong treatment, but you're willing to tolerate those mistakes because on average, you will make, you know, in expectation, you will make more money. I guess if you had a decision maker who really was uncomfortable with that level of error rate, you could actually build in some loss aversion into the profit function, but we haven't done that because firms are not supposed to be loss averse. All right, step 3, you run the test and you collect the data. So that can be done with any A/B testing tool. You don't need any modifications to the testing tool. So for those of you who are wondering about dynamic approaches, if you have a dynamic approach, it has to interact with the medium and be constantly updating the treatments. But this, I have done a test and roll in Gmail, literally. Like, well, I used a Google Sheet to do the randomization, and then I sent the Gmail in a mail merge. So it doesn't, what I'm trying to say is that the test enroll framework works very nicely with existing testing platforms. Step 4, you deploy the treatment with the higher average profits. You just compute your averages. Oh, there, I do know how to compute averages with tidyverse code. For those of you who don't know me, I've been doing R for like 15 years. And so I'm very good at base R and very bad at the tidyverse, and I kind of hate it. I kind of like have a secret hate of Hadley Wickham for having taken the language I knew and made it into a different language.
And I would add the same applies to ggplot.
Yes, I hate ggplot too. As well, I hate ggplot too as well. But don't tell Hadley if any of you know him. I know he is a huge supporter of R ladies, and I actually think his work is amazing. And I love the R for Data Science book. I'm just an old lady who can't learn new things. All right, so you deploy the thing with the higher treatment, and all of that's just 4 steps, and that was just 5 lines of code. Now, of course, I'm cheating a little bit because I'm using functions that I wrote, and I used stan, and there were a whole bunch of lines of code in that stan model. And depending on what kind of data you have for that meta-analysis when you go to plan the test, you need a different model. So we have 3 examples in the paper that have 3 different MCMC setup, 3 different stan models set up for different settings where you only have the data in aggregate, or if you have the raw data, all that kind of stuff. All right, we're doing perfect on time. So there's a few more things you should know. One is, we already talked about, which is you can have different priors for A and B. And so here, if you make mu, you can make mu like a vector of length 2, and sigma a vector of length 2, and S a vector of length 2. And that means you have, the first one is for the first group, and the second one is for the second group for all of those. And so I actually wrote this function, plot prior mean response, so that you can plot the priors if you like to see pictures. So there's treatment 1 versus treatment 2. So this is actually what you would be thinking about for a holdout test. So if you're running a paid media against a holdout, you probably have some prior beliefs that the paid media is better than not sending the paid media. Otherwise, you wouldn't be paying for it. We actually have, the data set in the paper turns out to be the other way. The catalogs do sometimes depress sales, maybe because they have like ugly pictures of models in it or something, I'm not sure. But in general, as marketers, we think that if you send someone an ad, that you might have a prior on that ad that looks like this blue line. Like, I'm not really sure how well it works, might not work at all, but it probably works quite a lot. And then I might have this prior as the profit I would get in the control condition where I don't send them that advertisement. And it's usually like a little tighter because I kind of know how my customers typically perform. And the question is like, how much better, how much can I move them up with that treatment too? And then you can pass those vectors for mu and sigma and S. So now mu is a vector of length 2, sigma is a vector of length 2, S is a vector of length 2. You run that test size function. You can't use the formula. Instead, it does a numeric optimization and tells you that the optimal test size is 641 versus 2549. So you actually want to put more test in the advertisement for 2 reasons. One is you think that advertisement is profitable, so you might as well put some more sample in it. And then the second reason is that you're not very sure about it. So because you're not very sure about how well that ad performs, you want to do a little bit more sample in the test so that you can figure out what's going on with it. And so there's the optimal sample sizes for we call this the asymmetric case. I don't know if that's a good name. You guys should tell me in the chat if that's a good name, the asymmetric case. All right. The other thing I wanted to tell you about was I promised you I wouldn't talk too much about hypothesis testing, and I've tried to stick with that, but I do want to tell you why you should never do hypothesis testing for an A/B test. There's a bunch of things that can go wrong with hypothesis testing when applied to A/B tests, and I feel kind of like I did the other workshop. I always kind of feel like a fraud when I'm doing a workshop on hypothesis testing, because I'm like, I really don't think it's a very good fit for A/B testing. So why? Well, one is you can end up with recommended sample sizes that are larger than the available population, and that's just kooky. Like, well, you shouldn't run a test if you don't have enough population. That doesn't make any sense. Like, some data's got to be better than no data. The other thing you run into with hypothesis testing applied to an A/B test is you can get the null hypothesis significance test can say it's non-significant, which means there's no difference between A and B, or there's no detectable difference between A and B. So what do? You're still going to pick the one with the higher average. You might collect more data, but it's kind of weird in that framework to do that. So it puts you in a weird spot. Another thing that's weird about hypothesis testing is that in most marketing settings, type 1 error doesn't matter at all. So if A and B are the same, but you decide that they are different and deploy one of them, you have lost absolutely no profit because they were the same. So why are we worried about that kind of error? So type 1 error just like isn't important in this context. And then the last thing is it's hard within the frequentist framework to rationalize unequal test group sizes. So when I first saw a holdout test with unequal test group sizes, I was like, gosh, how do you decide? Actually, someone once asked me, you're a statistician, how big should the holdout group be? And I was like, it's optimal to make it 50-50, so I guess it should be 50-50, and that's obviously illogical. So under this framework, using asymmetric priors, you can come up with a rational answer for how big should the control group be, which is something it's very hard to do in the frequentist framework. Of course, some of you are biostatisticians, and I hope that you do not give up on hypothesis testing. So the way I see it, kind of just at like a high level, is that hypothesis tests are designed for science. You want to know which treatment is better with high confidence. You kind of want to declare a winner for all time. You want to say, like, does hydroxychloroquine work or not work? And you don't want to, take the risk of a deployment error because you're potentially deploying, say, a medicine to the planet. And that has big implications. So you want these bigger tests. In science, you don't usually explicitly consider the cost of the experiment. It's usually small, so small relative to what you're planning to deploy to, that the cost of the experiment is kind of not something you really need or want to consider. And you generally want to have much larger sample sizes. So I think that's a perfectly fine inferential framework for science. But test enroll is designed for marketing, where we want to select treatments that maximize profits. We actually care about the cost of the test relative to the error rate, and we're okay. We can tolerate some error. And like, really, if you get the wrong subject line on the email, nobody dies. It's okay. So on average, you want to play the game to play the odds, whereas in science, you really don't ever want to make a mistake. And then we like the idea that it's the small sample sizes scale to small advertisers that just simply don't have access to larger populations. So that is all I have for tonight. I can't wait to see what all the questions look like. Are there any questions we should handle now at the end, Ron?
I think it's actually...
How long is the document? Is it like...
it's long.
It seems like it must be very...
Five pages.
Wow.
But I think it's actually a great, like, now that we covered everything, if someone wants to ask a question, just turn on their video or just speak and ask, now is a good time for overarching questions and things like that. Because most of the questions are just technical, what does this mean or what does that mean?
Oh, okay. Okay. So they're asking, yeah, you can tweet out the, you're fine with tweeting the Google Doc, right, Ron?
I think so, yeah.
Yeah, it's open to the world. Okay, I'll tweet it afterwards. Let's see. Just a few things like kind of to point you in other directions. So if you don't like R, I assumed everyone here tonight would be somewhat okay with R. But if you don't like R, we built a Shiny app. So this is actually that test size NN function turned into a Shiny app. And it actually compares it to a hypothesis test. And you can get this little table. Down here where it says Thompson sampling, that's comparing to Thompson sampling, but it's not been implemented yet. So it's there, but not quite there. We have a row for it, but we don't actually compute it yet. And
when we say Thompson sampling, this is a version of the multi-armed bandit or reinforcement learning, which is kind of easy to implement, and almost every company we know actually uses today.
Yeah. All right. If you want to kind of dive into the details, you can get to the paper. And I think what I linked there is, so the paper is published and behind a paywall, but I linked the second to last version before the final version that's on a preprint server. For those of you from Biomed, SSRN is the Social Science Research Network. It's sort of like our version of arXiv. There is complete replication code for the paper, and it's actually in the same repo where this workshop is. So like every figure in the paper you can reproduce using that replication code. You don't always have the real data, so it won't be perfectly the same, but you can get the idea. And then there's the link to Chris Syed's blog post outlining a similar approach that's framed as discounting.
So there is one question coming in, is that does the Shiny app assume all priors are normal, or the parameter, like what are the assumptions the Shiny app implements, I guess?
Oh, it's just the normal. It's literally the same function as the normal, which I explained kind of what the assumptions are in that. And I don't think it does the asymmetric because there's no.
Not yet, yeah.
Not yet. So that's a summer project for us. Except the summer is half over, so it's maybe next summer project for us.
So Ellie, maybe I think because we have a few minutes, I think it's like these questions kind of came back again. Okay, suppose you don't have a normal two-armed example, right? Like they have 3 arms, I have beta, I have something else, etc. What do you do, right? Because our formulas just wouldn't like directly apply to that.
So I think we have code for the 3-arm case, but we have to check it.
Right.
But that's like, it's essentially doable with numeric optimization. If you don't like these priors, so, and this is something you and I went back and forth a bunch of times on. So we have implemented a beta binomial version. So if you're a true Bayesian and you really want the model to reflect the data generating process.
And the data is convergence, right? So it's 0, 1.
That's all implemented. There's in the repo, there's another file called functions_BV, and that's a beta binomial version. And of course, then assuming that the S is true, we don't need to do that. And assuming that we know the S is known, I didn't mean to say true. So assuming that S is known, you don't need to do in the beta binomial version, and we can optimize that. And there's actually something in the back of the paper where one of our reviewers was really a true Bayesian, was like, why aren't you using the beta binomial? So we ran comparisons, and you get the same answer for all kind of reasonable sample sizes that we see in marketing cases. But if you have a situation where you might be looking at like 1 or 2 successes in the test, then you really should run that beta binomial version. I'd say less than 10 successes in the test, then the normal approximations. So, Ron is a true believer in the central limit theorem, and he believes that it happens relatively quickly, and he's mostly right. So you can use that normal model as an approximately accurate model. But if you're a true Bayesian, we have that beta binomial model. Now, if you had a completely different model, I have to think through what, like,
you can do it, right? You can
yeah,
write.
you just compute the profit. Like you sample from that prior that you have and you compute the profit over and over for a bunch of samples. And we could probably set up stand generated quantities to do that. Like you don't use the model portion of the stand block, so you can actually use stand to simulate. And we could probably do that. So that, I think that's doable. If you're interested in doing that, like definitely stay in touch with us.
And you can kind of probably the intuitive way to think about it, you can draw, there was this graph that Ellie had shown that, we increased the sample size slowly and we calculated the expected profit. So this is basically what you're doing, right? You're saying whatever distribution you have, you're going to draw from it, you calculate averages, expectations, you increase the sample size a little bit, and you draw this graph and say, oh, my maximum is in this point. So for my prior and my data or my expected data, this is what I will use. It's, of course, it's less elegant than, a formula, but it will work, and it should work pretty well. And with the technology we have today, it will work also pretty quickly.
Great. All right. So you might be wondering what's next for me and Ron. So we would like to turn that nnfunctions.r file into a package, but of course we have to write documentation and test, we should probably test those functions and all that kind of stuff. We are working on improvements to the Shiny app, and we're also working on a new paper that is on latent stratification for marketing experiments. And I wanted to mention that because if you're someone who has experiments where the response is a number, but there's a lot of zeros, this latent stratification can actually increase the power of the test. So it's an analysis technique. Test enroll is a test planning technique primarily. This is an analysis technique that basically can get you tighter posteriors on your estimates of the average treatment effect for a test. And there are versions of that paper out in the world if you Google our names. So that's all I had. And we're right on time.
Thank you. This is like a wonderful workshop, and not only workshop and also the Q&A sessions, and a lot of people can participate. And we have 5 pages Q&A. This is our longest Q&A we have ever had. And thank you so much. We have recorded, and if anyone wants to rewatch the we take this workshop, we can go to our YouTube channel, and we'll post it there.
Great. Thank you so much for organizing to Our Ladies. You guys, for a volunteer organization, you guys put on a really great show. Anyone who is an interloper in Our Ladies, I encourage you to make a donation to Our Ladies because they do great work.
Thank you. You also advertise for us.
Of course, I'm a marketing professor. That's what I do. All right. Thank you.
All right.
Thank you, everyone.
Thank you, everyone.